Hello and welcome to this 8th lesson on functions and their derivatives. In the previous lesson, you discussed the property of maxima and minima of functions. You looked at the criteria for finding maxima and minima of functions and used that criteria to apply it to very practical problems. In this lesson, we are going to discuss two theorems. Both these theorems involve the derivative of a function and they are extremely important. They shed light on properties of functions. Let me try and motivate you towards the first theorem. Suppose I have a function defined on a closed interval a b, a finite closed interval a b, and suppose its graph looks like this. If you look at the graph of the function, some things are quite evident. First of all, the function is continuous in the whole interval a b. You can also see that the derivative of the function exists in the whole interval a b and therefore certainly in the open interval a b. And you also see that the function takes the value 0 if f is the function, it takes the value 0 at a and is also 0 at b. And now if you look at the graph of the function, you will find at least one point where the derivative will be 0. In other words, at that point the tangent will be parallel to the x axis. I think the point over here is quite evident. This is the point. Of course, there are other points over here where this happens. This is not an exception in this situation. This property is true of any function which satisfies certain very simple criteria. This is known as Rolle's theorem. Let us take a look at Rolle's theorem in its proper form. Here is what Rolle's theorem has to say. Let f be a function defined on a closed and finite interval a b taking values in the real line such that f is continuous on the closed interval a b, f is differentiable in the open interval a b, and f of a is equal to f of b is equal to 0. Then there is a c in the open interval a b such that the derivative of f at c is equal to 0. This is an extremely important theorem, as I have already told you. If you once again look at the graph that I had drawn for you, you will notice in that graph that this function is equal to 0 at the endpoints. Its graph is smooth so that the derivative exists everywhere. And then when the function starts, when you look at the graph, it starts from a and goes all the way to b. The graph has no option but to bend in such a way that at some point the derivative will be 0. That means the tangent will be parallel to the x axis. It has to happen. This is what Rolle's theorem has to say. Now, if you look at this theorem, it already tells you that if you have a function satisfying f a equal to f b equal to 0 and if it is differentiable in the open interval, continuous in the closed interval, the derivative must be 0. That in itself tells you that here simple criteria ensure that the derivative of the function must be 0. Let us see what we can do with this. First of all, let us look at it from the point of view of some routine problems. I have a problem here for you. Let us see. I have to apply Rolle's theorem to this problem. I have given a function, namely sin x minus sin 2x on the closed interval 0 to pi. Let me first verify if Rolle's theorem is applicable over here. Certainly sin x minus sin 2x is continuous in the interval 0 pi closed on both sides. In fact, it is continuous on the whole real line. Also, this is differentiable on the open interval 0 pi. In fact, it is differentiable on the whole real line. Further, you can check that at 0 sin x is 0 and sin 2x is 0, and at pi sin pi is 0 and sin 2 pi is 0. Therefore, the function is 0 at 0 and is 0 at pi. Therefore, it satisfies all the criteria of Rolle's theorem. Hence, by Rolle's theorem there will exist a c in the open interval 0 pi such that the derivative of the function will be 0 at c. Well, what is the derivative of the function? That is cos of c minus twice cos of 2c. That must be equal to 0. Rolle's theorem ensures that there is at least one such c. Well, how do you find that c? Suppose I put cos c equal to t, then this equation becomes t minus twice, and cos 2c can be written as twice cos square c minus 1. So, this becomes twice t square minus 1 equal to 0. If I solve this quadratic in t, and it is no difficult matter to solve this quadratic, you will find two values of t equal to 1 plus or minus under root 33 divided by 8, and t, remember, is cosine of c. So, I get cosine c equal to this. Consequently, c will be equal to cos inverse 1 plus minus under root 33 divided by 8. It is cos inverse of 1 plus minus under root 33 divided by 8. You must make sure that this value of c certainly lies in that interval that we are discussing, namely 0 to pi. You will find that it does. And so, this function that we discussed satisfies the properties of Rolle's theorem, satisfies the conditions of Rolle's theorem, and we have been able to find a c whose existence was also guaranteed by Rolle's theorem. Let us take a look at another exercise. Let us look at this function e to the power 1 minus x squared on the interval minus 1 1 closed on both sides. This is the composition of two continuous functions, the function 1 minus x squared and the function exponential, and therefore, it is a continuous function on the closed interval minus 1 1. Since both the functions 1 minus x squared and exponential are differentiable on the whole real line, this function is certainly differentiable on the interval minus 1 1. You can also check that this function takes the value 0 at minus 1, it takes the value 1 at minus 1, and it takes the value 1 at 1. Therefore, this function also satisfies the conditions of Rolle's theorem, and hence there exists a c such that the derivative of this function at that point c will be 0. What is the derivative of this function? The derivative of this function is minus twice x into e to the power 1 minus x squared. And so, by Rolle's theorem, there will be a c where this derivative will be 0, and c lies in the open interval minus 1 1. So, by Rolle's theorem, there will be a c such that minus twice c e to the power 1 minus c square is equal to 0. We know that the exponential function is never equal to 0, and therefore, minus twice c must be 0, which implies c is equal to 0. Well, that is the c whose existence was guaranteed by Rolle's theorem. There is another theorem which is called the mean value theorem. This theorem generalizes Rolle's theorem. In other words, Rolle's theorem is a particular case of this theorem. Let us first take a look at the statement of this theorem, then we will discuss it. Let f be defined on the closed finite interval a b taking real values such that f is continuous on the closed interval a b and differentiable on the open interval a b. Then there is a c in the open interval a b such that f b minus f a upon b minus a is equal to the derivative of f at c. Why is this theorem called a generalization of Rolle's theorem, or why is Rolle's theorem a special case of this theorem? The reason why Rolle's theorem is a special case of this theorem is because if you take f of a equal to f of b equal to 0, then you will get the left hand side in this equation as 0, and you will find that the derivative of f at c is 0, which is what Rolle's theorem tells you, and therefore, this is certainly a special case of Rolle's theorem. Why is it called the mean value theorem? Well, this expression on the left hand side is actually the mean value of the function in the interval a b, and what it tells you is that the mean value of the function in that interval is really equal to the derivative of the function at some point in the open interval a b. What is a geometrical interpretation of this theorem? Let us take a look at that. So, I have the x and y axis, and I have a function from the interval a, from the point A to the B, whose graph looks like this. What the theorem says is that if you take the straight line joining the endpoints of the graph, then there will be some point on the curve where the tangent will be parallel to this straight line. You can check that at least one point is guaranteed over here. This tangent is parallel to this line. That is the C which is ensured by the mean value theorem. There is of course another point where this will happen, but there is at least one point where it will be parallel to the line joining the endpoints of the curve. And the mean value theorem has tremendous applications. It is of great importance to analysis, and it throws tremendous light on properties of functions. Let us take a look at some problems connected with the mean value theorem. Here is the first problem. Let us take a look at the function log x on the closed finite interval 1, 2. This function certainly satisfies the properties of the mean value theorem. It is continuous in the closed interval 1, 2. Log x is certainly differentiable in the open interval 1, 2. And so, by the mean value theorem, there will be a point C inside the open interval 1, 2 such that log of 2 minus log of 1 divided by 2 minus 1 will be equal to the derivative of the function. The derivative of log x is 1 by x. So, there will be a C in the open interval 1, 2 such that log 2 minus log 1 by 2 minus 1 will be equal to 1 upon C. This is ensured by the mean value theorem. How do you find that C? Well, log 1 is 0. So, this really boils down to log 2 equal to 1 upon C, and therefore, C is equal to 1 upon log 2. You can check that 1 upon log 2 lies in the open interval 1, 2. It just takes simple routine checking to do that. Let us take a look at another problem connected with the mean value theorem. Find a point on the parabola y equal to x minus 3 squared where the tangent is parallel to the chord joining 3, 0 and 4, 1. So, you are required to find a point on this curve y equal to x minus 3 squared, which happens to be a parabola, and this point should be such that the tangent at that point is parallel to the chord joining 3, 0 and 4, 1. Remember, 3, 0 and 4, 1 are easily seen to be on this curve. And if you look at this, this function over here certainly satisfies in the interval 3, 4 the criteria for the mean value theorem. And therefore, by the mean value theorem, I would get the value of the function at 3, which is at 4, which is 1, minus the value of the function at 3, which is 0, divided by 4 minus 3 should be equal to the derivative of the function at some point C. The derivative of x minus 3 squared is twice x minus 3. So, at C the derivative will be twice C minus 3. From here you can easily find the value of C. Now, how does it relate to our problem? See, the left hand side is nothing but the chord, the left hand side is nothing but the chord joining the points 3, 0 and 4, 1, the slope of that chord, and the right hand side is the derivative of the function at the point C, and therefore, it is the slope of the tangent at the point C. And so, the slope of the tangent at the point C is equal to the slope of the chord joining 3, 0 and 4, 1, and therefore, the tangent will be parallel to the chord joining 3, 0 and 4, 1. So, you can see that the mean value theorem helped you to find this point where the tangent will be parallel to the lines joining the endpoints of the curve. Well, let us look at some more applications of the mean value theorem. It has substantial applications even at this elementary level of school. Here is the first application that I have in mind, which is slightly out of the routine. Suppose I have a function f defined in an open interval a, b, and such that the derivative of the function is equal to 0 for all x in the open interval a, b. Well, I claim that the function f is a constant in this interval a, b. How is that? Suppose I take any 2 points x and y in the interval a, b, x and y fixed, and let us look at the closed interval x, y with x less than y. Now, if you check, because the function is differentiable in the open interval a, b, it is certainly continuous in the open interval a, b. Since x, y is inside the open interval a, b, it is continuous in the open interval a, b, and differentiable in it is continuous in the open interval a, b. Therefore, it is continuous in the closed interval x, y. It is differentiable on the open interval a, b. Therefore, it is differentiable in the open interval x, y, and so it satisfies the criteria of the mean value theorem. Well, what does the mean value theorem say? It says f of y minus f of x divided by y minus x must be equal to the derivative of the function for some point c between y and x, but the derivative is 0 everywhere. So, f y minus f x by y minus x is equal to 0. Since y minus x is positive, I get f y minus f x is 0, which means f y is equal to f of x. This just means that for any x and y, f y is equal to f x, and therefore, the function is a constant. But there is something I must tell you over here. Let me just illustrate it here. Suppose I have a function defined on 2 open intervals, so that the graph looks something like this. If I take the domain to be the union of these 2 open intervals, the function is certainly not a constant, but the derivative is 0. So, you must understand that our theorem or our result over here, which is an application of the mean value theorem, only says that if the derivative of the function is 0 in an open interval, then in that open interval the function will be a constant. That must be borne in mind. Here is another application that I have of the mean value theorem. You must remember, long ago we discussed in one of our early lessons that if the derivative of a function is strictly positive in an open interval, then the function is a strictly increasing function. We did not prove that result over there. We very briefly indicated some ideas which might constitute the proof. In fact, I told you specifically this is not a proof of that result. Now that we have the mean value theorem, we can prove that result in no time. Here is how we prove it. Well, suppose I have a function f defined on this open interval a, b, and suppose the derivative is strictly positive in this interval. I have to prove this is a strictly increasing function. Once again, take any x and y in the interval a, b with x less than y. Look at the closed interval x, y. The function being differentiable in the open interval a, b is continuous in the open interval a, b. Therefore, it is continuous in the closed interval x, y, differentiable in the open interval x, y, because it is differentiable in the open interval a, b, which is larger than x, y. So, the criteria for the mean value theorem is satisfied. By the mean value theorem, f of y minus f of x upon y minus x will be equal to the derivative of f at c for some c in the open interval x, y. But remember, the derivative is strictly positive. So, f prime c is positive, y minus x is positive, therefore, f y minus f x is positive. This simply means f of y is greater than f of x, which is what we had to prove, that the function is strictly increasing. You could also use the mean value theorem to show that if the derivative is strictly negative in the open interval a, b, then the function is a strictly decreasing function. There are other applications of the mean value theorem that we would like to discuss over here. Well, now that you are familiar with the mean value theorem and Rolle's theorem, and as I told you, Rolle's theorem is a special case of the mean value theorem, let us just go back to Rolle's theorem for a while and just look at one application of this particular case of the mean value theorem. Suppose I have a polynomial p of x with real coefficients, say alpha naught plus alpha 1 x plus polynomial of degree n. And suppose I know two roots of this polynomial. That means I know two zeros, say a and b. So, the polynomial is 0 at a and is 0 at b. A and b are real numbers. All these coefficients are also real numbers. Then by Rolle's theorem, there will be a point c in the open interval a b where the derivative of the polynomial will be 0. So, c belongs to the open interval a b. Well, what has Rolle's theorem done for you over here? Rolle's theorem has helped you to be able to locate, at least to some degree of approximation, the root of the derivative of the polynomial. If you have a polynomial, very easily you know that the derivative of the polynomial is also a polynomial. So, the special case of the mean value theorem has helped you locate a root between two roots of the polynomial p x. We have located a root of the polynomial p prime x. Of course, we do not know what the root is, but we know that it lies in this interval a b, where a and b are roots of the polynomial p x, and it lies in the open interval a b. That is also of importance over here. So, we do have some degree of approximation for where the root lies. Coming back to the general mean value theorem, here is another application that I have in mind for you. Let us take a look at this. Suppose I have a function f for the time being, say defined on the whole real line. This is not necessary, I could just restrict myself to open intervals, but and suppose this function is such that it is differentiable on the whole real line and the derivative is bounded. The derivative is bounded by some constant, say capital A. In that case, this is what will be true for the function. For any numbers y and x, f of y minus f of x will be less than or equal to a times mod of y minus x. This is known as a Lipschitz condition for the function, and it is very easy to derive. Let me just show you how it is derived. It is a simple application of the mean value theorem. This is what I need to prove. I need to prove mod of f y minus f x is less than or equal to a times mod of y minus x, where f is such that its derivative is bounded by a in absolute value. Well, take any y and x with x less than y, then you can see, because the function is differentiable, it is continuous in the closed interval x y, differentiable in the open interval x y, and so by the mean value theorem, f of y minus f of x divided by y minus x will be equal to f prime c for some c in the open interval x y. Now, all you need to do is take the absolute value, both sides. Then mod f prime c is less than or equal to a, and then just take mod y minus x to the right hand side and you have your inequality. As a very special case of this, if you look at the function sin x, for instance, then you can see from here, because sin x will satisfy the criteria that f does, that mod of sin of x minus sin of y will be less than or equal to mod of x minus y. You can check this very easily. For any real numbers x and y, this will be true. Mod of sin x minus sin y is less than or equal to mod of x minus y, because the derivative of sin is cosine, which is always bounded by 1. So, the a that we had would be equal to 1. Well, let me discuss one other application of the mean value theorem with you. Here is what I want to tell you. Suppose I have the function f of x equal to e to the power x. If you remember, we are aware of this inequality, e to the power x is greater than or equal to 1 plus x for all real numbers x. With the help of the mean value theorem, you can derive this inequality in no time. Also, if you think carefully, you will find that this equality over here will hold if and only if x is equal to 0. How do we derive this inequality? Well, let us just take a look at the function f of x equal to e to the power x, and let us take a look at the interval 0 x for some positive real number x. So, x is some positive real number for the time being, I am taking x to be positive. Then e to the power x minus e to the power 0 upon x minus 0 will be equal to the derivative of exponential function at some point c in the open interval 0 x. Now, exponential c will always be greater than 1 because c is greater than 0. So, I will get e to the power x minus 1 upon x is greater than 1. Let me just write it over here for you. This just implies e to the power x minus 1 because e to the power 0 is 1 upon x is greater than 1. Because x is positive, this just reduces to e to the power x is greater than 1 plus x. You can similarly derive an inequality when e to the power x is negative, and you will find that it will be a strict inequality. So, equality will only hold when x is equal to 0. One last application of the mean value theorem. Suppose I have a function f defined on the whole real line and a function g defined on the whole real line such that the derivative of f at any number x is greater than or equal to the derivative of g at any number x. Further, suppose f of 0 is equal to g of 0. Then this is what will be true, f of x is greater than or equal to g of x for positive x. How do we prove that? Well, consider the function h of x equal to f of x minus g of x. If you look at this function h of x equal to f of x minus g of x, then you will notice that because the derivative exists on the whole real line, it satisfies the criteria of the mean value theorem in this interval 0 x. And you will find h of 0, h of x minus h of 0 upon x minus 0 will be equal to h prime c, the derivative of h at c for some c in the open interval 0 x, and h prime c will be nothing but f prime c minus g prime c, which because of this condition will be greater than or equal to 0. And so, because x is positive, I will find h x is greater than or equal to h of 0, but h of 0 will be 0 because of this criteria. So, I will just get h of x is positive, h of x is non-negative, and therefore, h of x being f x minus g x, I will get f x minus g x is non-negative, which means f x is greater than or equal to g x. Well, I hope you enjoyed all these discussions with the mean value theorem. In the next lesson, we shall be discussing tangents and normals. Thank you.